Hi, please get out your science journal, and today we're going to be talking about volcanoes and hot spots, which is everybody's favorite topic. We're going to start by looking at an example, a classic example of a volcano, and I want to point out what's happening here. We have molten rock spewing out of a fissure in the ground. It looks like fire. These look like sparks. They're not. They're molten rock, and these tiny little bits that look like sparks are actually tiny bits of molten rock that then cool in the cooler atmosphere and harden and become smaller fragments of solid rock, in this case probably cinder, and that's forming what we call a cinder cone. You often will have lava flowing depending on the consistency of the magma, and if it's got more metals in it, for example, it's got a lower melting point and it will flow smoothly. That's one type of volcano. Another type of volcano is what we call an ash volcano. And again, the word ash can be misleading because ash and lava are not the same thing as the ash in your fireplace. There is no fire coming out of a volcano, although the material that is coming out of the volcano is extremely hot. What is coming out of here are, again, tiny, tiny fragments of molten rock that are then crystallizing into these tiny little bits called ash. It's not like the ash in your fireplace. They're tiny bits of volcanic glass. The reason why this volcano is creating ash while this volcano is creating lava, again, it has to do with whatever its magma consists of. It has a lot of quartz in it that has a really high melting point, and the only way that it will flow is often in an explosion. There's also gases like carbon dioxide and even water that are forced into solution, and those will also cause an explosive reaction, sending ash high into the atmosphere. So much friction can actually create lightning. This can be caught up by winds and change global climate. Big clouds of these will flow down the side in these mud flows called lahars that can move at supersonic speeds. So volcanoes are a little bit frightening. Some things that volcanoes are not, however, there is no, for example, baking soda and vinegar. That's a chemical reaction, and that's unfortunately a common activity that people like to do to mimic a volcano, but the problem is it doesn't really capture the essence of what a volcano is. Because what a volcano is a vent or fissure in Earth's surface through which magma and gases are expelled. And so what we're going to state here is that a volcano equals a escape of molten rock and gases. And the other thing that I want you to note is that this, as they melt, they harden. As they reach the Earth's atmosphere, they harden and they actually can become new crust that solidify and harden into new crust. So the idea that lava spews fire is a nonsense idea, but it does spew extremely hot materials that, say, when they come in contact with things like forests. So here is lava flowing into a forest in Hawaii, and it is in fact igniting the trees because they're flammable. But the lava itself is not the same thing as fire. And despite the fact that we use words like ash, that's not what it actually is. So at the very heart of it, all a volcano is, it's not necessarily a mountain even. In fact, all volcanoes start out as not mountains. And I'm going to show you this terrific video of a place in Mexico called San Juan. And it is southern Mexico down here. And in 1943, a very big surprise occurred while a farmer was out in his cornfield. And this young man is actually recording himself visiting this place, and he's going to tell us the story of it. So, enjoy.
In 1943, a farmer here in the small town of San Juan was tending to his crop like normal farmers do. And then in between his corn, a 2-meter crack opened up when he was working. Shortly after, plumes of sulfur-smelling smoke started erupting out of this crack. He ran to town and told everybody what happened. Later that night, that crack opened and started spewing tons and tons of sulfurous ash and buried the town.
Can you imagine?
Fast forward 60 years and the town looks like this. Completely covered in volcanic rock. All that's left is the church of San Juan. Just the tower. Everything else is buried under meters and meters of jagged black stone. This is the story of Volcán Paracutin and the city it swallowed.
So there's the cinder cone in the background. This is a young man who probably is now an old man watching this cinder cone that was once a cornfield. So what does it take to be a volcano? Again, just an escape of molten rock and gases. And in places where molten activity or where heat is below the crust, new volcanoes can emerge, like at Paracutin in Mexico. Kind of a crazy story. So we've talked about volcanoes up to this point, and I want to just review some of the examples of what creates volcanoes. So one example is subduction zones. The crust is being subducted. Parts of the crust are too light to integrate or to melt into the to recycle into the mantle. There also are wedges of sediments that may get caught up in this, and so they'll melt and rise up, forming this island arc. And just for another new vocabulary word, just to clarify what that is called, we call that a convergent boundary. And a convergent boundary, if you would please say those words, refers to a plate boundary where two plates move toward each other. And so if we're going to add to our notes, volcanoes form at one is a convergent boundary in the form of island arcs. And when we look at some of the volcanoes around the world, you can see they're very, very concentrated right next to where the trenches are, and those are subduction zones. Okay. So another place that we've observed volcanoes forming are these mid-ocean ridges. And of course, this is where magma is coming up very close to the surface, creating new crust. And here you see again these little volcanic eruptions. And this is an example of a divergent boundary. Can you say those words? It's a plate boundary where two plates move away from each other. And of course, in the process, you have volcanism taking place. So divergent boundaries, and those are just new crust forming from in the spreading centers. Okay, so those are the two types that we've already discussed. But when we look at the volcanic map of where volcanoes around the world are. Again, we can see that some of them are clustered along spreading centers, but then there's this phenomenon of these random volcanoes that seem to be in the middle of the plate. And I'm going to focus in, for example, on Hawaii. Hawaii is right here. It is literally in the center of a huge tectonic plate, where there's clearly neither convergent nor divergent boundary. So what's going on here? To explain this phenomenon of volcanoes randomly being in the middle of plates and not anywhere near divergent or convergent boundaries, we're going to add a new vocabulary word. That word is hot spot, and that's probably pretty easy for you to say. So what happens in a hot spot? It is a plume of heat rising from the mantle, melting overriding crust, and causing ongoing volcanic activity in that spot. So what does this look like? Well, I want to remind you of the fact that crust on the Earth is constantly in motion. And most of the average rate of speed of crust on mantle moving is about the rate that your fingernails grow, fascinatingly enough. And I found this terrific GIF here that actually is inside a volcano where the surface of it is cooling. It's sped up. It's cooling into rock. And it's like a sped up version of plate tectonics on our Earth. So you have heat rising up from below. You have spreading centers, you have subduction zones. It's really fantastic examples. So remember that the crust is always in motion, and yet these hot spots are in one place in the mantle. I don't really know why. So here's a great GIF showing that. Here's your heat plume coming up. This is obviously sped up. The plate carries the volcanoes away from the hotspot. And it says, at a hotspot, a magma plume, called a hotspot, stays still while the plate moves. The hotspot punches volcanoes through the plate. So this volcano formed when the plate was right over the hotspot. You can see it is now, its feeder tube is emptying out. It goes dormant. Eventually it goes extinct. And then it's just a high mountain that's just there to be eroded. And that's what eventually forms these things called seamounts. As each volcano moves farther from the hotspot, because the plate is moving over the hotspot that birthed it, it erodes away until just stubs remain. And this is what you can see of Hawaii. So Hawaii, the biggest island, is the one that's directly over the hotspot, and that's called the Big Island. That's where all the volcanic activity is. They get smaller and more eroded as you move away until eventually they go underwater. And you can see that the plate has moved quite a bit over this hotspot over millions and millions of years. This chain of seamounts is thousands of miles long. And originally, this was the spot that was over this hotspot here in the mantle. And you can see that the plate then moved north, creating these seamounts. And then eventually it took a turn and it moved west. And the seamounts continued to kind of march off to the east. And fascinating fact, right off to the east, a new volcano underwater seamount is forming. It's an underwater volcano, and it's the freshest island. Wait a few million years, and it'll be the new volcano. The new Hawaiian Big Island. So we have hotspots, which are plumes of heat rising from the mantle, melting crust, and forming volcanoes. So, lest you think Hawaii is the only place in the world with hotspots, let me just clarify that is definitely not the case. There are hotspots all over the world. Hawaii is one of them. The Galapagos are another. We can go see those in the southern part of the Pacific, right on the equator, and they're actually part of Ecuador, the country. Another one, as you can see, is in Iceland, and you can that's the reason why you can actually go stand literally on the mid-ocean ridge, because there's been a hot spot over that part of the mid-ocean ridge for long enough that it's actually created so much volcanic activity that the Rift Valley actually runs right through Iceland, and you can go and stand with 1 foot on the North American plate and 1 on the European plate. It's pretty exciting. And then one more that I want to point out here is good old Yellowstone. And so let's go head over to Yellowstone in northern, whoa, that was trippy. Didn't mean to do that. In northern Wyoming. And we've talked about Yellowstone before. It can be a little scary because it's considered a supervolcano. It's very, very big. But I want you to notice on our geologic map here that it's actually a patch this patch of pink basalt that kind of marches off to the west as the plate has been moving over it. And here it is now. That's the active part of Yellowstone, and you can see Yellowstone is full of all kinds of geysers as the groundwater gets heated up by the magma below and explodes out, and hot springs, just like you also would find geysers in Iceland. And so the last thing that you'll be doing today is using this fantastic map to put some hot spots on your map. And I would really encourage you to particularly draw the seamounts marching across the Pacific of Hawaii, because that's such a classic way of like tracking the plate movement over the top. Thank you.